Hi everybody. We are going to keep going today in chapter 11, and we're going to look at something called the integral test. Make sure that you're all caught up on the previous two sections in chapter 11 because we use a lot of the concepts from earlier. So before you start this, make sure you're caught up or it'll be, the notation might be confusing. Alright, let's jump in. So what we're going to be doing is comparing a series to an integral. So what we're going to, just to show you how it works, I'm going to do two quick back-to-back examples. They're the same ones in the book. They're good examples. So if we have the sum from 1 to infinity of 1 over n squared, it's just this, right? And we want to know, does it converge or diverge? So the way that we defined convergence of a series in the previous section is that we look at convergence of the partial sums. So here's your Sn terms the partial sums. Now it turns out there's no simple formula in this case. Now we saw earlier that if you had a telescoping sum or something, there's simpler formulas. Here we don't have one, but you can always make a table and just look at it. So every time we increase n by doubling it or multiplying it by 5, the sum doesn't seem to go up very much. So that tells us it's probably convergent. But that's not good enough, right? We don't know at this stage whether a sum converges or not. So we're going to need to prove whether it converges or not. So what we're going to do, we're going to compare our sum on the previous slide to the area under the curve of the function 1 over x squared. We're just going to imagine each term in the sequence is the area of a rectangle. So look here. So every term is the area of a rectangle. Remember, sequence is the individual numbers. The sum is called the series. So if we do a right endpoint approximation, when we plug the number 1 into the function, we get 1. When we plug 2 in, we get 1 over 2 squared. Plug in 3, get 1 over 3 squared. So the heights of the rectangles are determined by the function, by the right endpoint approximation. And what we can see is that if we can show that this integral converges, that will mean the sum converges, because the sum is definitely less than the integral. So what we're going to do is we're going to ignore this little bit over here. What we're really interested in is, does this thing converge if you go to the right in the long term? We're not interested in the convergence of what's here. That's an improper integral. We're not interested in that right now. We know that this area is 1. And then we're just going to use the integral from 1 to infinity to approximate the rest of it. Right? So there's the sum of all the rectangles. And it's the same as our series, right? That's exactly the same as the series we started with. And if we exclude the first rectangle, remember, we know the size of the first rectangle, so we can just ignore it for now. The total area of the remaining rectangles is smaller than the area under the curve, which we saw from the picture. And the area under the curve is the value of the integral, the improper integral 1 to infinity of 1 over x squared dx. So when we did improper integrals, back in section 7.8, we actually saw that this integral is in fact convergent and has value 1. So instead of going through all the calculus for this, we're just going to refer you to a previous section if you want to see it. You should be able to do this integral at this stage in the class with 4 weeks to go or 5 weeks to go. So all of our partial sums, so as we move to the right, adding up rectangles, it has to be less than this. This is the size of the first rectangle, the 1 by 1, and this is the size of the integral. So this is 1, so together they're 2. So no matter how many terms we add, it has to be less than 2. And if these sums are always less than 2, then they're bounded by 2. They might be bounded by something smaller, but we don't know what that is. But we know for a fact, just because of geometry, they can't be bigger than 2. We also know that they're increasing. So anything that's bounded and increasing, because every time you move to the right, you're adding a rectangle whose area is bigger than 0. And we saw the monotonic sequence theorem back in section 11.1 that the partial sums will in fact converge. So the series is convergent. So if it's bounded and monotonic, it has to converge to a value. We really don't care what the value is. We just, all we did here is show that the value exists and that it's something. And that's enough for us to say that the sum converges. So it turns out that it's actually pi squared over 6, which is might seem a little strange. There's, on the Wikipedia page, there's about 50 proofs if you want to check them out. If that's your sort of thing, if you like high-level math stuff, go ahead and click there on the PowerPoint and check it out. There's a whole bunch of proofs that the sum of this series is in fact pi squared over 6. But for our purposes, we just care that it converges to something. We don't really care what it is. So now we're going to look at a different series. This is 1 over square root of n. Again, no simple formula. But as we, either multiply by 2 or multiply by 5 with n, we're not seeing this thing sort of converge and settle down on any particular value. That doesn't mean it diverges. It means that we suspect that it diverges. So we should investigate. So we're going to do another comparison to an integral. Same thing. We're going to have each term is going to be width 1 and the height determined by the function. Here we're going to use a left endpoint approximation. Our function is y equals 1 over radical x. So we can see that the area of the sums, right, as we add it up, is always greater than the area of the integral from 1 to infinity. So if we can show that this integral diverges, it'll show that the sum diverges. So the rectangles are exactly our series. We can see the rectangles is in fact larger. I just went over that. Now let's do the math on this one. We hadn't proved this one yet, sort of like in class. I did the 1 over x squared in the notes, but I didn't do this one yet, so let's do this one. Again, you should know how to do it, but let's go over it. So this is an improper integral. Right? Add 1 to the power, divide by the new power. And we can see what happens here, right? This is just 2 squared of b. When we plug in infinity here, we get infinity minus 1, which is infinity. So this integral diverges. And because the integral diverges, that tells us that the sum diverges, because the sum is always sitting on top of the integral. So we saw 2 different examples. We saw one where the sum is less than an integral that converges, and the sum is bigger than an integral that diverges. It turns out that it doesn't matter if you use a left or right endpoint approximation. The rule is called the integral test. You just need either a right or left endpoint, and whatever happens to the integral happens to the sum. That should make sense based on how right and left endpoints work. So let me go through the integral test, then I'll go back and explain why it works. I'm not proving the integral test, but I'm just explaining why it works. The proof is in the textbook. But I'll give you sort of like the overall sort of how the proof works. So I'm not going to ask you to prove this on a test. All right, so we need a continuous positive decreasing function. Right, continuous because we can integrate it. Positive because we need it to be less than some particular value. So it can't be negative. And decreasing because it has to be bounded and monotonic. And we're going to let each term be, the function evaluated at some n. Again, whether it's left or right endpoint doesn't matter. If the integral 1 to infinity of f of x dx is convergent, then the series is too. And same thing here. If the integral 1 to infinity f of x dx is divergent, then the series is too. Now there's a couple of things going on here that I'm going to point out on the next slide. One of them is that it doesn't matter what the lower index is. Normally we make this a 1. It really honestly does not matter. And that's explained here. The integral and the summation do not need to start at 1. If you're not sure, just put a 1. Any real number can be used for the lower limit of integration or the initial value. generally speaking, you want to start at the lowest at 0, but for the integral, you definitely could go negative. For the sum, you can start at 0. And also note f does not need to be decreasing on its entire domain, but does need to be ultimately decreasing for x larger than some number n. So it just means eventually it needs to decrease. So if you end up putting the wrong number in the lower bound, it's not going to make a big deal. Just understand that you can pick just some number sufficiently far to the right. As long as it's continuous positive decreasing from that number on, you're good to go. All right, so I'm not going to prove the integral test. I'm just going to tell you why it works. So let's go back and look at our rectangles again. So I'm just going back to this slide. So let's say I decided to do a right endpoint approximation instead of a left, which would make the sum less than something that diverges. And you would think, well, if it's less than something that diverges, we can't learn anything. But it turns out it doesn't matter, and here's why. A right endpoint approximation of this is the same thing as taking all of these rectangles and pushing them 1 unit to the left. Right? That's all it would do. It would just move this rectangle to here, move this rectangle to here. Right? So, because we're taking this limit to infinity, pushing everything 1 to the left does not change the overall sum. Right? So if you need to think about it, think about what if we took 1,000,000 terms, right? We'd push everything 1 unit to the left, and we'd tack on that 1,000,000th rectangle. Well, 1 over square root of 1,000,000 is 1 over 1,000. So you're not adding very much area. So the difference between a right and left endpoint is a finite amount, and it's a very small amount because we're looking at what's going on to the right. So that's why it doesn't matter if it's a left or right endpoint approximation or a midpoint approximation. It doesn't make any difference. The reason that I did the 2 illustrative examples here is just to show you that it should make sense based on the geometry. But if you think about shifting these rectangles 1 unit to the right or left, it doesn't change the overall size very much. Certainly not the difference between converge and diverge. All right, so again, the proof is in the book if you want to check it out. It's a little detailed, but it's basically what I just explained. All right. Well, let's pick up where we left off. So we were looking at an example. So we just want to determine convergent or divergent. So first thing you do is you check the function. So f of x, 1 over x squared plus 4, you have to verify that it's continuous positive decreasing. You can do that with a graph. Clearly it's continuous because there's no division by 0. Clearly it's positive because x squared is always positive. How do we know it's decreasing? Well, what you would do is take the first derivative and show that it's negative. I'm not doing that right now. I'll let you guys work on that on your own if you want. But if you have some funny function, you're not sure about it, either draw a graph or take the first derivative. This first derivative is in fact negative. So we can use the integral test. So you just write this as whatever the starting summation index is, you just put it here. 1 to infinity. Again, this doesn't need to be a 1. You can put any number here as long as it's like, you really want to go bigger than 1. Like 1 or larger. It's an improper integral. We just use the formula. Right, this is just an arctan formula that you should have memorized. It's on the list of formulas to memorize, for sure. So we just push the limit inside. Arctan of 1/2 is just arctan of a half, so I'm not worried about that. So we push the limit in here. So arctan of infinity over 2 is just arctan of infinity, which is just pi over 2. So there's your answer. Right? It's pi over 2 minus arctan of a half. I distributed the 1/2. So I got pi over 4 minus 1/2 arctan of 1/2. Comes out about 0.554. And what you just have to recognize is if this is a finite number, it doesn't matter what the number is. But if this integral is a finite number, then the series converges. And it's going to be close to that number. Could be an overestimate, could be an underestimate, but it's going to be close to that number. But all we're interested in here is convergent or divergent. So this, the integral converges, so the series converges. And that's the integral test. But you need to check continuous positive decreasing. On an exam, if you don't check it, you're going to lose points. All right, so let's do another one. Here we have cosine of pi x over square root of x. And what conclusions can be drawn about the series. So you want to check, are these x's the same places that the n's are? They are. So this series is just this function with n's plugged in instead of x's. That's what we want. Now we have to check continuous positive decreasing. So I made a graph, and I saw that it's definitely continuous, but it certainly is not positive, and it certainly is not decreasing. That means we cannot use the integral test. So if you run us into a situation like this, where you can't use the integral test, you have to stop. Because we don't have a way of evaluating this. All right, let's do another one. Find the values of p for which this series is convergent. Here I'm starting at 2, because if n is 1, then we get division by 0. So I'm just starting at 2 here. So I made a graph of different values of p, just to see what it looks like. I tried 4 values of p. It was continuous positive decreasing for all the p values I tried, and also starting at x equals 2 and above. There's actually a vertical asymptote at x equals 1, so I didn't start there. So it looks like it satisfies the integral test. So let's use the integral test. So I just rewrite the summation as an integral. Of course, it's an improper integral. Here we have a u substitution, right? Because you can see there's a 1 over x. So u is just ln of x. So it's a pretty easy u substitution. Don't forget to change the bounds to u. And then because we have 1 over u to the p, that's just u to the minus p. So you go up a power, so just add 1, divide by the new power. Plug in ln of b and ln of u. I pulled the 1 over 1 minus p to the front because it's a constant. It's a constant depending on p only. Our variable here, like it was u, and now it's b, right? B is sort of still a variable. But p is no longer a variable. P is a constant. We just have to pick a number for the constant. So I know we went from x to u to b to p. I know there's a lot going on here. But once we've done the integral, we can treat p as a constant. So what I did here, just to make it's a lot easier for me to think of exponents as being in denominators and being positive. So what I did is I just took the reciprocal. So I just did ln of b 1 minus p is just p minus 1. Remember, when you go into a negative, when you make a power into a denominator, it just make it negative. So I just flip the signs on 1 minus p to make it p minus 1. For me, this is a lot easier to think about in terms of algebra. Now I can really see what's going on. This is a constant. This is a constant. Once you've chosen p, it's a constant. And we can see, just looking at it, that p is not allowed to be 1. We figured that already, but just looking at it, we'd have 1 over 1 minus 1. We'd get division by 0. So we're either looking at numbers bigger than 1 or less than 1, but it can't be 1. So what I noticed is, because these are constants, that really all I have to worry about is this. In other words, if this diverges, then the constants don't change whether it diverges or not, right? Diverge plus a bunch of constants or times a bunch of constants is still diverge. But if it converges, a convergent sum times a constant is still convergent. A convergent sum minus a convergent sum is still convergent. So these two constants don't factor in anyhow into whether it converges or diverges. So I'm just going to look at this part right here. And what you see is that when you plug in b into the plug in infinity, natural log of infinity is infinity. So any infinity to any number bigger than 1 stays infinity. Infinity to any number smaller than 1 might get smaller. It still might be infinity, but it still gets smaller. So what I was thinking about here is just I tried some numbers, and if you plug, so again, p is not allowed to be 1, because infinity to the 0, again, not defined. But for example, if you plug in 2, infinity to the first power is still infinity. If you plug in, for example, 1.1, infinity to the 1.1 minus 1 is still infinity. So again, infinity to any positive power is infinity. So this thing is going to converge. Like 1 divided by infinity, the limit is going to some finite value. This thing might end up being 0. But this is a constant, so it converges. Now, if you plug in a number less than 1, so if I plugged in, let's say 0, I'd have 1 over infinity to the minus 1, which puts it in the numerator and just makes it infinity. So it diverges if p is less than 1. So where does it converge? Only for p greater than 1. And because this little part here converges, that means this whole thing converges. So this whole thing converges, right? Because convergent minus a constant converges, times a constant converges. And if the integral converges, that means the sum converges. And you're done. So you have a couple problems like this on the homework. Make sure you know how to do these, and make sure you know how to reason your way through sort of the limits and the numerical quantities. All right, let's keep going. Last thing we're going to look at today is how to estimate the sum of a series. This is probably the most useful thing that the integral test does. As we progress through Chapter 11, we're going to learn a lot of different tests. And the integral test is definitely one of the easier ones to use. And it's really the best one for estimating the sum of a series, if you can use it. Suppose we have been able to use the integral test to show a series is convergent, and now we want to find an approximation to the sum S of the series. We can use any partial sum because the limit of the partial sums is the overall sum. So a partial sum is a good approximation, but is it good enough? That's what we're going to be looking at. How accurate is the estimate? So what we need to do is look at what's called the remainder. So the remainder, we're going to use capital R, and it's going to be the actual sum S minus the partial sum. So what that really is it's all of the terms in the series after n. So it's an plus 1 plus an plus 2 plus an plus 3, and so on. So we pick a value for n, and we say, well, we're at least as close as the rest of the terms, because the rest of the terms have to be less than some sort of integral. So we're at least that close. And what we call Rn the error. So it's the difference between our estimate and the actual value. So everything's the same as the normal integral test that we just saw. So needs to be continuous, positive, decreasing. Here we're not decreasing on 1 to infinity, it's n to infinity. And we can see here with these rectangles that, you know, if here's n and the an sum less than that this converges. And we can go the other way, right? We can see that if we use a left endpoint approximation, it's just an plus 1. So this is what I talked about earlier. The difference between a right and left endpoint approximation is just scooting all of the rectangles down 1 unit, right? So look at this graph. See, an plus 1 is a right endpoint, and it goes from n to n plus 1. So its width is still 1, and its height is just f of an plus 1. And here we just took all the rectangles and scooted them down 1 unit. So what this tells us is that the difference in the estimate, so the remainder, has to be somewhere between the left and right endpoint approximations. Because one of them is an overestimate the whole time, one of them is an underestimate the whole time. And the reason that works is because the function is decreasing. So for the right endpoint approximation, all of the rectangles are below the function. For the left endpoint approximation, all the rectangles are above. So if Rn is always bigger than this and smaller than this, then we can actually pin it between these two integrals. And so this is the remainder estimate for the integral test. So continuous, positive, decreasing, and we need this to be convergent, right? If the sum diverges, then we can't use this remainder estimate. You would just get infinity. So we're just saying the remainder is the difference between the sum and the partial sum. And again, this is always, when we start to the right, this is always smaller because it's like one less rectangle, basically. And here, starting at n, is like one more rectangle. So this is always bigger because it's a slightly bigger, but it's always bigger. All right, let's see how to do this. So that's the formula we're going to use. And I'll show you in the example how it works. So we're looking at the sum from 1 to infinity of 1 over n to the 5th. This is a 3-part problem. We're going to sum up the first 10 terms to estimate the overall sum. Then we're going to use our remainder estimate on the previous slide to improve our estimate in part A. And then we're going to use the remainder estimate one more time. We're going to find a value of n that will ensure the error in the approximation is less than 1 in 10,000. Sorry, 1 in 10 million. So very precise. How precise can we get this? How many terms do we need to go to the right to ensure that our estimate is below that, that value? Well, let's start with part A. Summing the first 10 terms is not that hard. And notice that 6 decimal places. Now, we pretty much know this is an underestimate, right? Because without being told otherwise, this is a right endpoint approximation. But we can get a better estimate by using the remainder, the estimate for the remainder. So I'm just recopying the formula here. Now what I'm going to do is write what Rn represents. It's actually S minus Sn. And we're interested in finding, well, what S is. So we're just going to add Sn to both sides. Well, going to add it to all 3 sides, I guess. And then here's what we do now. So we have the partial sum plus the left endpoint approximation, and then here's the right endpoint approximation. So all we do is we plug in all the known values. So we've already seen, like, for example, this is Sn right here. Right? We just computed it. It's S10, right? Then we have to do this integral from 11 to infinity of 1 over x to the 5th. And here we're going to do it from 10 to infinity. So I'm just, on the next slide, I'm just plugging all the known values in. I went ahead and computed these integrals, rounded them to 6 decimal places, and then you add, and you're done. So you can see that the accuracy is much higher here. So this was only 10 terms, and we are within 1, 2, 3, 4. We're good to 4 decimal places. Looks like it's really close to 5. So if you only need 4 decimal places accuracy for some sort of project or something, you use the integral test to get your accuracy by just adding rectangles. All right. Well, adding some rectangles and then tacking on in 2 integrals, right? All right, let's do part C. So part C says we need this integral to be less than this. Let's talk about why this is not n plus 1. If you look at the construction, the n plus 1 is always less than s. We need to make sure s is less than some value, so you want to use n here, not n plus 1, because it's stuff to the right. So I did the improper integral here. Again, that's something you should be able to do. You get 1 over 4 n to the 4th. That has to be less than 1 in 10 million, so this is just that. And you just solve the inequality, and you get n is greater than 40. So if you need 4 decimal places accuracy, maybe you need 9 or 10 terms. To get 7 decimal places accuracy, you need 40 terms. And that might seem like a lot, 40, but it's really not. Any applications this would be used for, a computer would be doing this stuff, and a computer doing an operation 40 times does not take long. All right, well, that's it for this video. If you got any questions, let me know. And in the next video, we're going to continue on with Chapter 11 and look at the comparison test. All right, till next time, see you all later. Bye-bye.